Next up is Peter Ward. He's coming down. And Peter's going to talk about assessing the impact of man-made underwater noise for new renewables in the outer Pacific.
Yes, it's in there somewhere. That's how do you use this? Just there. Right, thank you very much, Mr. Chairman. My name is Peter Ward. I work for Kongsberg Maritime Limited. Apologies if some of you have already seen something very similar to this in other exhibitions. Some of you may be a little bit surprised to know that Kongsberg Maritime are involved in underwater propagation studies. Hopefully at the end of this presentation you'll be able to revise your views about that. This is actually a case study that we did on behalf of Aquamarine Renewables with regards to their waste-to-wave energy device. This was a study that took place between 2 and 3 years ago, and there were really three components to this. Underwater noise measurements, we'll explain a little bit about the how and the why of that, underwater propagation modelling, and finally acoustic impact modelling. The next few slides will put a little bit more meat onto that skeleton, but bear that structure in mind and then you'll see how the whole thing begins to fit in. Now, traditionally when you go out and measure underwater noise, background noise, before any development takes place, what you've done in the past is to trail a hydrophone behind a vessel for a period of a few hours or a few days, and you can get transect measurements of the underwater noise levels. This tends to be very expensive because boat hire isn't cheap, even when you've got a private company to pay for it. And also there's going to be a whole bunch of artifacts, acoustic artifacts that appear in the data, which are a bit difficult to deal with if you're not sort of expecting them. Things like wave slap on the side of the vessel, wave strum, or cable strum rather, where the cable with the hydrophone on begins to vibrate like a violin string. You can filter a lot of that out, but there are other ways of actually doing underwater noise measurements. And Kongsberg developed a seabed recorder called RUNES, Remote Underwater Noise Evaluation System. And this was a large device. It's about 1 metre diameter, stands about half a metre high from base to the top of the hydrophone cage there. And it's designed to sit on the seabed for extended periods at a time. Fairly wide frequency range. We actually used a combination of 2 hydrophones. There was a small high-frequency hydrophone there and a larger spherical hydrophone contained within this free-flooding orange dome. We could get RUNES to sample on various sampling schedules. For this particular work, we were sampling the noise levels for 2 minutes every 2 minutes every 30 minutes for an overall period of around 6 weeks. So, where did we go with this thing? You'll recognise this bottom figure as being the northwest coast of the Isle of Lewis. This puts the whole picture into context. On this scale, Stornoway is just about down here, so not too far, and I think there's going to be a tour later onto this site later on in the week. The 2 units were deployed for around about a period of about 2 weeks, and they were in water depths of 25 to 30 metres. We used 1 RUNES unit in each of the little dark project areas, which were the areas defined to us by the client Aquamarine. Now, we had about half a terabyte of data to process once we got the things back. And this is an example of some of the data. This was an ensemble of 10 1-second pieces of acoustic data. The reason we averaged the data in this particular way is because if we just looked at 1 second snatch, the whole spectrum would be impossibly hairy and you simply wouldn't be able to see any detail in there. But once you've smoothed it in this particular way, we see a lot of features that are conform to people that have studied underwater background noise for a long, long time. So, for instance, we see that wind and wave noise is predominant in this region. We also get rain noise somewhere around about here. And from time to time on individual samples, you can see much higher tonals, which are associated with passing vessels. but when you look at slightly longer term averages, tonal noise, ship noise, begins to smooth out. We found that the total noise levels over the two sites were 119 dB, plus or minus a little bit of variation, and 117 dB, plus or minus a bit more variation. We discovered that, or we realised that the differences between the two levels over the two sites weren't hugely significant, but you could probably attribute them to differences in local wind and wave conditions, local bathymetry, any noise artifact that passed by one site and not the other. But as I say, we don't think those were particularly significant. So the second part of this, the acoustic propagation modelling. This is demonstrated by what I... Oops, all right. Oh dear, it's stolen my thunder. By the cause and effect modelling. And if you imagine it as a sort of a bit like a sort of a mincing machine in a way, we've got this sound being modelled on one side here, and on the other side we get some sort of impact on the environment, whether it be marine mammals, human divers and swimmers, fish, or something else. And what ties the cause and effect together is the underwater propagation modelling. And this shows a whole bunch of environmental parameters that feed into this particular process that come from oceanographic and acoustic databases. Now, just a few words about the model. Firstly, I come from a physical and mathematical background, so apologies if you're feeling a little bit worried when you see these sort of heavyweight mathematical expressions. But what I want to sort of draw to your attention here is acoustic propagation modelling is a mathematical process, and it has its roots in a lot of sort of fairly abstruse algebra, where you start off with such things as the inhomogeneous wave equations in Cartesian or in cylindrical coordinates. Don't get too concerned about that. In order to get some sort of answer with regards to the propagation of sound out, what you have to do is to determine the nature of the problem that you're trying to solve, whether it be high frequency or low frequency sound, whether you're looking at shallow water case, deep water case, or whether you're looking at acoustic near field or acoustic far field. And that directs you to one of a number of different model approaches. Ray theory and parabolic equation. Ray theory is good for high frequencies and long range. Parabolic equation is good for low frequencies and relatively short range. And you can actually mix and match the results from two different modelling processes, as long as you're a little bit cautious about how you interpret the results. The only one that doesn't come from manipulating the wave equations is the energy flux theory. This came from a British scientist who carried out about 40 years worth of experiments on sound propagation in shallow water seas, and came up with a theory that pretty well works in about 75% of cases, but that's a slight exception. Moving on, the sort of data that is fed into the propagation modelling is pretty well common regardless of the sort of model that you use. And it falls into one of three groups. First, you need detailed information about the bathymetry. For the acoustic modelling that I did here, I looked at a number of different transects centred about one particular location. I think there were probably about 36 transects here. And for this, I used the bathymetry information from ETOP01, which is a global database, has a resolution of 1 minute resolution. Some of you may be familiar with this. The oceanography data, that came from World Ocean Atlas 2009 vintage. And from that, I was able to construct sound speed profiles for 2 points of the year. This is the summer sound speed profile, and this is the winter sound speed profile. And the different nature of these profiles dictates to some extent how far and how wide the sound spreads from the source point. Seabed geoacoustics came from British Geological Survey charts and also client-commissioned geological and geophysical surveys. And in fact, we found that there was a good degree of correspondence between the two sets of results in that case. So we can get a whole bunch of parameters that enable us to populate the propagation model. And this is just an example of the sort of propagation modelling results that we can get from each. Top one is propagation looking downslope, so this is going from the coast into the ocean. Whereas on this one we're looking upslope, so we're looking from the wave energy converter site inland, very much shorter transit, only about 2 kilometres there. The blue, that corresponds to the background noise levels that we got from the earlier background noise survey. Here we see the source level, well, can't quite see it on this particular scale, but we see that this sound fairly uniformly decreases in intensity as you move out in range, although it's not uniform throughout the whole water column. We see that there's relatively quiet zones for 1 or 2 metres closest to the water column, and there's sound geoacoustical reasons for that. I won't go into that because there really isn't time. But to see this sort of distribution of sound in range and in depth gives you an idea of how various different animal species may begin to be impacted by the resulting sound. As I say, this was for drilling noise, and I've got a whole bunch, in fact dozens of these plots for drilling noise, for operational noise, different months of the year, and so on and so on. Now, how do we work out the impact on marine life? This is the third part of the overview that I introduced right at the beginning. And this is a whole bunch of information that's been compiled over the years by various different researchers that have determined sound pressure levels and sound energy levels that are likely to give rise to some level of impact on a particular marine organism. And I've sort of colour-coded them for ease of sort of interpretation. It's a bit like a traffic light system, but there's no green is okay, you can go. It's all sort of bad news from an animal's point of view. Lethality and permanent deafness, we simply don't want to go there at all. And there are reasonably well-established sound pressure levels and sound exposure levels that begin to indicate the onset of permanent deafness or even lethality. Temporary deafness, TTS, temporary threshold shift, there's a whole range of particular values depending on whether we're looking at cetaceans, pinnipeds, or more in particular, harp porpoises. And less than that, or at lower sound pressure levels, but by no means less in significance, are sound pressure levels and sound energy levels that indicate behavioural changes. And for the interested reader, you can check out some of these references. I have it on good authority that Southall's seminal work in 2007 is going to be updated and released sometime in the next 12 or 18 months. So we could well see that some of these change in significance and in appropriate sound pressure level values. So how do we get from those to impact ranges? Well, we take, for instance, the sound pressure level 180 dB. We look at the propagation plots that I showed earlier, and we find out the maximum range at which the 180 dB level is crossed. And we find that, and we can do that for various different of the impacts. And we find that for drilling and for operational noise, neither sound was loud enough to create lethality. You're not going to kill the animals there. You're not going to give them permanent deafness or temporary deafness. Harassment, that's a particular version of harassment which comes from the American authorities. We see that depending on the level of background noise, and we can see that the background noise can vary between plus or minus 6 dB, about the mean value, then level B harassment can occur either not at all, if you're in a really noisy background, out to 97 metres, or operational noise out to 65 metres. So, to conclude, we can see that operational noise and drilling noise for the wave energy converter sites off the west coast of Isle of Lewis doesn't give rise to any significant impacts. The behavioural impacts are possible, but we say that dependent on background noise, they may be there or they may not. We would say they're deemed minimal and manageable, and there's ways and means by which you can get round those sort of fairly minimal events. And as a result, the Oyster project received consent just about a year ago, not entirely due to the acoustic impact study, I hasten to add. There was a whole bunch of other studies that really supported the consenting. Now, I'm sure you appreciate that in a time slot of about 10-15 minutes, there's a very limited amount that I can say, and there's a whole bunch of other subjects that I simply didn't have time to cover. Characterisation of noise sources, temporal and spatial variability of acoustic propagation, cumulative impacts, fish. We've seen that Tony's got some very good ideas on fish impacts. But I'm certainly happy to talk about any or all of these over a coffee or even a beer later on. Thanks very much for your attention.
Thank you, Peter. We've got 10 seconds. Can I just ask a question? This is a wave energy.
Sorry, out of time.
This is a wave energy site, so the surface will be crinkly. Does that have any implications if you've got a several metre swell on the sound propagation on the site?
Absolutely, it does. Yes. What I did was to look at the typical case with regards to sound propagation, so I can put in a sort of a crinkly wave surface, and that has the effect of creating a diffuse sound field where pointed sound sources, as we've seen here, are unlikely to propagate as far as they would if the surface was plain and smooth. The worst possible case is, on an absolutely fine day, the sound can propagate relatively long distances, but equally, you probably wouldn't be generating operational noise from a wave device on those sort of days, so it sort of swings and roundabouts.